If it gets streamed, then well and good. So now let's just focus. Okay, so am I present? No, right? Okay, so wait, let me remove the blur. You can see this, right? We gotta start from the start. What is this?
King of Hearts.
Queen of Hearts.
Yeah, so right, King of Hearts. So how did you all come to a conclusion that this is a King of Hearts? What features?
The number and the symbol.
Pardon, I didn't get that.
The number, but like the K and the heart.
Yeah, sure. Also, how did you all come to know that it's a card? What features of a card did you all observe?
Size, design.
Right. Also the four sides, right? It has four sides. So that was for the card. Apart from that, since there's a king, you all understood that it's a king card. Okay, then there is heart. So it's a king of hearts. So this is how our brain processes things. So what it does is it tries extracting the most obvious features first, and after that, it goes on finding the smaller details. So even if you all read a sentence, right, that might have a word or a two as some errors, some typo, it's most probable that you all will end up reading that sentence properly, even though there's some minor typo. Because that's how our brain works. It goes on focusing, upon the major features, okay, and then it goes on focusing the minor features. So if then even if like it goes to identify that error, it will be quite later when you read that sentence for two times or three times. Okay. So that's basically image processing in our brain. How our brain goes forward to process the image. All right. So in machine we call it convolution neural network. So convolution basically means like having to extract the features from that image. Okay. So there's a function called convolution function that we basically study in the second year. So let's go back. So I'll start with the architecture. Okay. Hmm. So okay, so now if you all see an image, right? Take any image. So an image is basically made up of pixels. Okay, if it's a black and white image, it's just a single layer. If it's a colored image, then you have multiple layers, right? So there's red, okay, there's blue, and there's green. So these are the three layers that together give us the different colors, right? The combination of these three colors, primary colors, go forward to give us the different colors. So what we do, okay, so let's consider a single an image that has just shades of gray. That's a black and white image. Okay. So what we do is each pixel can either be black or white. So when it is white, we keep it okay. We like assign that pixel a value of 0, and when it is black, we assign it a value of 1. So say we had some image, okay, and then that image is converted into this matrix. So each of this is a single pixel. All right. Consider this to be a single pixel. Now here that pixel was white, so we put a 0 over here. Then here it was white again, so we put a 0 over here. Now here in this case it was black, so we have 1 over here. The screen is uh, presented right to you all.
Yep.
Okay. Okay. So what we do is we convert, and basically an image is a 2D matrix, okay, or a 2D array. So when we represent it with numbers, it turns out to be a 2D array. So once we have this 2D array of an image, what we do is, okay, we multiply it, multiply in a sense, we convol it with a feature detector. Now, what is a feature detector? A feature detector is a matrix that is usually smaller than the original image. Okay, it can be 3 by 3, it can be 5 by 3. There's no restriction upon the dimension of that feature detector. So what this feature detector does is it is basically applied on this image, okay, using the convolution operation to give us a feature map. Now, feature map is basically a more refined version of the image, okay. So it's like the image, we have an original image, we apply the feature detector to extract the important features from that original image, okay, and then we end up getting a feature map. So how does this happen? Okay, I'll explain in brief. I guess it's, I mean, okay. So if you see here, this is a feature detector, right? A single feature detector. This symbol represents a convolution operation, and over here is our original image. So now what we do is we take this feature detector, and just to give you all a visual representation, we take this, place it over at the start, okay, from the first cell itself. So this one is placed over here, this one is placed. We just overlap it, okay, and this is the original image. Here nothing is replaced, okay. This is the actual original image. So this is our input. Okay, this is the feature detector. And basically convolution operation, you all can go through this. I'll give you all the link. Okay. So what we do is we take this, we place it over this. And what we do is for each single cell, right? See, for this first cell and this one's first cell, we basically multiply it. Okay. Let me I'll show it on the this mobile. Screen is visible, right? The mobile screen. Is it visible?
No, I don't think it's visible.
Just- It's saying that I'm present. I lost connectivity. Just give me. I lost connectivity already. The hotspot got disconnected. Uh, is it visible now? Is my screen visible now? Am I there?
Am
Is
I
my
there?
other
Is
screen?
my other screen?
Because I can hear my
Because
voice,
I
but I
can
can't
hear
see
my voice,
anything
but
on
I
the screen.
can't see anything on the screen. It's visible though.
Oh.
Okay, cool.
Okay, so
Okay, so
uh,
uh,
great. It's fine.
great. It's fine.
So this is our
So this
matrix.
is
Okay,
our
this is our
matrix. Okay,
image
this is our
matrix.
image matrix.
So this is the original
So
image matrix. Okay. Then we apply the convolution operation using a feature detector. Okay. For now, we'll consider it to be a 2 by 2 feature detector. All right. So let's just consider some values 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, 1, 0. Okay. And then here we'll take a 1, 0, 1, 0. Is it visible? Because I can't see any changes. Hello. Are you there? Or did I get disconnected? Hello, hello, hello. Could you all
could
hear
you
me talking
okay.
before this? Hello. Can you all hear me? Hello. Am I audible? A thumbs up. Just give a thumbs up if I'm audible. Okay. So let's continue. We have this as our this feature detector. Okay, this is our feature detector, and this is our original image. Okay. So what we do is, so let's start from the beginning. Okay. So this is our feature detector, which is a 2 by 2, and this is our original image, which is a 4 by 4 matrix. So initially, we'll apply the feature detector on this part. Okay, since it's a 2 by 2. Now, what we do here is we multiply 0, this first cell, right? This first cell into this one first cell. That will give us 0, okay? Followed by the second one, this one into this one, again 0, this one into this one, 0, and this one into this one is 1, okay? Plus 0 plus 1. So, in the resultant, this matrix, okay, the resultant matrix is good. So, here the result is 1. So, we'll write 1 over it, okay? Now, what we'll do is we'll shift. Now this will be applied here, okay, over here. So again, do the same thing, okay, 0 into 1, 0 into 0, 1 into 0, and 0 into 1. So over here, we are going to get 0, okay. So over here, we are going to get 0. Now after this, once we do this, apply this on this. Now if you all see, this is like here it's 2 by 2, right? But here it's 2 by 1 by 2 by 1. So what is happening in this case is we are taking it like this, okay? So we are imagining that there is some value which we don't consider while calculating, okay? So just imagine this box extends over here. So what we do is 0 into 1 is 0. Here there is nothing, so just don't add, don't do anything. Then go here. This into this, okay? This into this, again 0. Here also there is nothing, so just don't consider it. And then we'll get 0, okay? So that comes over here. So similarly, you have to fill this table, okay? So now in the next step, what you'll do is you will apply this, okay? You will apply this on this. Okay, so now you came one step below, okay? Then after that, you will go to this particular box. Then again, the same thing. Then again, one step below here, okay, and then here. Okay, so this was to explain how the convolution operation is performed. Last time I couldn't explain this because I couldn't present using the mobile. Okay, so let's get back to our PPT. Okay, so if you'll see here, screen is visible, right? Yeah, okay, cool. So if you'll see here, they apply this over here, okay, they write a result. Then they apply this, the same feature director over here, okay. So they keep on applying it and they keep on filling this matrix, okay. So this one will get filled over time. So if you all see now they are here, then after that they'll shift here, okay. So it keeps on going till we reach this particular section, okay. So now what happens is, so you applied this feature detector over here, okay, on the last cell, and then we got our feature map. Now this was when we applied a single feature detector. Okay, so when you apply a single feature detector, you get a unique feature map. Now in the next, like not in the next step, we just don't apply a single feature detector. What we do is we apply multiple feature detectors in order to identify the various features. Okay, so if you'll see here, a single feature detector applied will yield a single feature map. So this one is a single feature map. Now behind this, there is another feature map that was basically, a result when we applied a different feature detector. Okay, so in this way we create multiple feature maps. So this entire thing, right? So this entire thing is called a convolutional layer. Okay, so convolution means we basically perform the convolution operation. Now also I'll give you a brief about the types of feature detector. So this one, this particular one, okay, here it is 5 by 5, but it could also be 3 by 3 because if you see the side, like the remaining values are 0. Okay, the main focus is on the smaller one. So if you see this particular one, we have negative five, negative one, negative one, negative one, negative one, and in between we have 5. Okay, so this is to sharpen the image. Okay, so if we apply this feature detector on a particular image, it will basically sharpen that image. Okay, then we have age enhance. Okay, so age enhance is negative 1 and 1. Then we have blur. So for blur, it's all ones. For the 3 by 3 matrix, 5 by 5 matrix, it's ones inside and outside it's a 0. Okay, so what this does, like if you look in the age enhance, it basically helps in detecting the ages. Okay, it makes the ages prominent over here. Okay, so each feature detector has its particular role. So this is the emboss feature detector, which helps in basically the textures. Okay, age detect again. So yeah, these are just the types of feature detector. Okay. So see, in the first step, it's basically extracting the features. Okay. Now, within the first step, you will also have rectified linear unit, which is basically like basically break the leniency. So when you're training the model on a particular data set, you don't want you don't want the model to be fitted to that particular training set. Okay, you want that model to be able to identify, like say suppose you are training your model on a particular image, like a data set of dogs. Okay, so you don't want that model to only understand those images that are present in the data set. Okay, say suppose you go and you put a different image as the input. Okay, once your model is trained, so you will want your model to identify that as a dog also. All right, so there's a section at the end of this particular lecture in cross entropy where I'll be talking about the way the model needs to be basically able to distinguish between the not distinguish or identify on the data that it has not been trained on. Okay, so at the end I'll basically go through it. So for now, okay, we have the first layer, that is the convolution layer. In that layer, we are basically basically extracting the feature. Okay, so when you extract, it is called convolute. Okay, so a feature map. Okay, an image is basically convolute to give a feature map. Okay, so that's the term. Then we have rectified linear unit in the first layer itself. So rectified linear unit basically breaks the leniency. Okay, so I'll give you an example. So if you'll see here, see this is the input image. Okay, so here we basically converted. So this is like age detect. So you can see we used age detect also with some amount of emboss. So like in short, what is happening here is this is a grayscale image. Okay, this one is a grayscale image, black and white. Okay, and shades of gray. So what we did is we represented black, we represented negative values by black, and we represented positive values by white. Okay. Now what happens in this image is why do like this basically is to help you all understand why we need rectified linear unit. Okay. So what happens here is if you see this part, right, this particular section, or even here if you see, there's like a linear trend. If that will, yeah. So what is happening here is, see, it is going, white is positive, black is negative. So what is happening? It is going from positive value, okay, it is slowly decreasing, then it's going to gray, and then it goes to black. Okay. So this is like a linear trend. If you see like on a scale, if I represent this, it will be like going, consider this to be a scale, okay, this particular line. So it goes from here to here. So it kind of tries to learn a linear pattern, which we don't want the model to learn. Okay. So say suppose in this particular section, okay, if the model in future needs to detect this particular section, say suppose it sees this white, say suppose it sees this white. Now what it will do is it will tend to expect some black over here, and if it doesn't get black over here, it will say that like say suppose in this case this is a building. Okay. So say suppose it learned this particular linear uh, pattern. So in future, if we go and put this image, okay, this particular section as an input, it will try to expect some amount of black over here. Okay, some amount of extreme negative values. But if it doesn't find, it will say like, okay, this is not a building. Okay, so it won't identify this particular object. So what we do is we try to remove any linear pattern. So if we see in the next image, so what we did is we applied rectify linear unit. So if you see here, this is the graph of this the red one. Okay, is my cursor visible? Yeah. So this red one is the graph of rectified linear unit. So if you see this is 0, okay, any value that lies before 0 has the y value equal to 0, whereas the values greater than 0 have their regular value. So if this was 1, okay, so y also would have some corresponding value, that is a positive value. So if you go here, all the black, right, all the dark part that represented basically negative numbers have been removed. Okay, so this is done using rectified linear unit. Just remember, in short, rectified linear unit is to remove leniency, and removing leniency is very important in terms of machine learning. Okay, because we don't want the model to be fitted to that training data set. For the mathematics, you all can refer. I'll give you these links. Okay, you can basically go through these papers. So now, after we do perform convolution, we come to the next part, that is max pooling. So now again, let's go back to how I do it. Okay. Now say we have this particular feature. Okay. See, this is a feature map. Okay. Now what we do is we pool this feature map. Now pooling means basically, okay, consider 2 by 2. So we take this 2 by 2. From this we take the maximum value. Okay. So what we are doing is pooling. So now within this particular matrix, we take the maximum value. So if you see this is 0, 1, 0, 5. Maximum is 5. So what we'll do in this pooling layer is we store this 5. Okay. This is basically a pooled map. Okay. So we'll store 5. Now what we'll do is we'll go to the next section. Now we'll see for the maximum value. Again, 5. Wait. Do we take this? Let me check. I just give me a minute. Mm. Okay. So what we do is we don't take this. We take, see, once this is done in the yellow box, we go to the next. Okay. Unlike in terms of in case of this, what was that? When we convert a layer, what we used to do, we used to take this one, and then we just used to shift one cell, okay, to the right. In this case, we don't do that. We shift it completely. So if a cell has been visited, we don't visit it again. Okay. So this was done. Now what we do is we come to this one. Okay. So in this, which is the maximum value, it's 4. So what we'll do is we'll store it over here. Okay. I know the matrix is a bit odd, but let's bear with it. Okay. Now in the next one, we go down. Okay. Now in this, it's the maximum value is 2. Okay. So in this, the maximum value is 2. And in the next one, this particular one, the maximum value is 1. Now this is a pooled layer. Now, what is the purpose of pooling? Like, what did we achieve by pooling? Okay. So consider this image. Okay. Consider this image. So this is a image of a smiley face. Let me divide it into 4. So see, this is an not photograph. Let me make this 8 so that I can explain. So now it's a 4 by 4 matrix. Okay. So what happens is, say this is our original image. Okay. Let's name it OR. Say suppose the same image we just rotate it. Okay. We rotate it 1, 2, 3, 4. 1, 2, 3. Okay, so the smiley comes here. Okay, then the other eye goes here, the other eye goes here. Now, what are the purpose of this? See, when it was like this, just consider this eye, okay? This particular eye. Let's just focus on this eye. When it was in this particular format, the eye was in this particular section. Okay, not eye. Let's go with this smiley face. Okay, let's go with the smiley face. It's easier to explain. Now, when it was here, okay, consider this part. In this cell, you see this section, right? Say the model learned that. Okay, the model learned that if you know in this particular box, if you see at one particular corner a curve, then like, okay, for this particular cell, it will mean there's a probability for it being a smiley face. Okay, then it will go to analyze this. Okay, for now, just to explain, consider this particular cell. Okay, so it will focus on this part. Now what happened is we give it an image that is rotated, the same image. Now this image is the same thing, right? It's a smiley face. It's just that this part has come over here. Okay, this part has basically rotated over here. Now the feature is over here in this, but according to our previously trained model, it was searching for this box. So if it comes at this box, okay, and it sees like this, okay, it's actually supposed to be like this. The smiley face like this. It is like this curve is located in the top half, but at the bottom of the top half. So it's like at the bottom instead of it being like this. Okay. So now what happened is only due to the rotation, the context of the image has changed for the model. Alright. Now the model basically doesn't have an idea. But say suppose we applied pooling. Say suppose we did a pooling of 2 by 4. So we considered this entire thing. okay, in the pooling map. So what happened is we got, say we pulled it, okay, we pulled the original image. So what I'll do is I'll take this section. Let's keep it at the side for now. Okay. So let's come back. So say suppose we applied pooling. Okay. We pulled this layer using a 2 by 4. Okay. I'm just taking this dimensions for example. Okay. So in 2 by 4, what happened? These two eyes, it said, okay, it's going to be in the top half. This smiley face is going to be in the bottom half. Okay. Over here. Over here. Now, if we give this image like this, what happened is, see, it got an eye over here. Okay. That means in the top half, it saw like, okay, there's an eye. So like, say suppose 50% chance. Okay. Here, since we are considering like a 4 by 4 metric, 4 by 4 dimensional matrix, the thing is it's just 50%. But as the dimension increases, the percentage and the accuracy also increases. Okay. So now here, since we are doing it by a 4 by 4 example, so it's just 50%. And if it looks in the bottom half, it will see that there is half of the smile. Okay, so half of this is present. So it will say like around 50% chance of it being, you know, a smiley face. So you have like around 50% chance. I know this is like half, but since our dimensions are also small, over here it's just 4 by 4. So that's the reason why this value is low. Say suppose take an actual image. An actual image is not a 4 by 4 matrix. Okay, it is like it has a quite larger value for the dimensions. So in that case, this value increases a lot. All right. So max pooling is basically to handle this case. Okay. So suppose the image is rotated or something has happened. Say suppose the smiley is like more of a smoke. So in order to understand that, we need to perform max pooling because it basically helps the model understanding the most important features. So to summarize, we had an original image. We applied a convolutional layer. Basically, the convolution function, we applied the feature detector to get a feature map. Or in general, like multiple feature map constitutes a convolutional layer. Okay. So this is like we got the feature. Okay, we extracted the features from the images. Now what happens in the next stages? We basically pool this. Also, to this convolution layer, we also perform rectified linear unit. Remember this, okay? To basically avoid linear pattern, basically avoid the model going further to learn a linear pattern. So just for that purpose. So then after that, we pooled a layer to like for the model to understand that in a particular like for a given feature map, what's the most important feature? Okay, so this resulting feature map, right? This resulting feature map will have the most important feature, okay, or the most prominent one. So for example, in the card example, like, right, so in that, what was the most prominent feature? The first is the shape of the object. So it had four sides and it appeared to be flat, even though you all couldn't tell about the depth. Like y'all could tell, but a basic machine couldn't tell about the depth. Okay, it could have just identified the four sides. So from the four sides, it could say that it could be a card, or it could be a mobile phone, or it could be a brick, because all these things usually have four sides. Then the next part you also was the heart or the king. Okay, from that you all understood that okay, this is a card. Okay, see, the first context was it just having four sides. Once you all went to the next part, when you all understood the next important feature of it having a king and a heart, you all understood it's a king of hearts and it's a card. Okay, so that's how uh, image processing works. Okay, and these things happen simultaneously. It's not like it will first look for the shape and then it will look for the heart and then it will look for the king. All the process happens simultaneously. Okay, so this is basically performing the max pooling operation. Okay, so here it does. So these are the steps. Okay, now the same summary that I gave you all. Okay, for the original image, we perform convolution to get this multiple feature map by applying multiple feature detector. So this is called a convolution layer. After that, we basically pool. So each feature map. So this is one feature map will be pooled. Similarly, the next feature map will be pooled. Then the next. So in that we get the pooling layer, which is the collection of all the pooled maps. All right. Okay. So I was supposed to show this website, but the thing is, this website is quite hard to get. Okay. Because if I go and click this link, it's basically redirecting me to some college. Okay. It will be present there, but I can't find it. If I find, I'll share the link. So this will help you all understand the multiple layers, okay, and how things are happening. So here it's five. So what happens is this is the original image, okay. After that, it applied the convolutional layer to get the feature map. So say a feature detector A was applied over here, and it got this feature map. Feature detector B was applied over here, it got this feature map, and so on. So we have multiple feature map. Now for this each feature map, we pooled it. Okay, pooled in a sense, taking the most important values. So if you see here, this is a more refined version of this. Okay, so even if you see there's kind of a linear pattern, even though it's not that prominent because it's not black and white. Okay, but still. So if you see here, we have a more, you know, refined version of this particular file. Okay, in terms of machine, so that a machine can understand. So similarly, here we pooled it, we got this, we got this, we got this. So this is like, it may be distorted to you all, but it's a pooled layer. So it's taking into account all the important features. Now what happens here is, again, we convolve this particular version, okay, of the pooled layer. So for this one, we apply a feature detector to get this version, okay, to get this feature map. Then we apply other feature detector to get this feature map, another feature detector to get this feature map. Okay, similarly we do for all. Then after that, again, see the thing is, you perform this step, you convolved, then you pooled it. Again you're convolving, again you're pooling it. Okay. Now in the next step you pooled it again, and after this, comes the next step, which I'll explain in the next step. Okay. So that's flattening. Now what happens is, see, this is your pooled map, right? Your pooled feature map. Now in flattening, what you do is you take this first row and you connect it to the next row. So if you see here, see 1, 1, 0, okay. Then the next is 4, okay. This 4, 2, 1. So what you're doing is you're basically connecting this to each other. So you're connecting this one to here, then this one's end you're connecting to this one's beginning, and in this way we get a 1D array. Okay, so the purpose of this is to convert this 2D matrix, okay, or this 2D array into a 1D array, okay, or 1D matrix. Now, why did we do this? What's the point of doing this? Okay, so you all understood why did we convolve it. Convolve is to basically get the features. Why did we pool it? Pooling is done in order to basically extract all the important features. Okay, then after that we flatten it. Now why do we do flattening? So the point of this is the next step, right, is giving this as an input to the ANN. Okay, now the ANN helps us in understanding patterns in this input data. Okay, so it will analyze this particular 1D array, okay, during its training, and it will look which node was active for what output. Okay, you all will understand in the further slides because there's a visual representation, so it will be more understandable to them. Okay, so what we did is we converted this 2D array into the 1D array, and okay, the next is, so this 1D array will basically act as the input layer for the next upcoming ANN architecture. So that's flattening. So again, I'll recap. We had an input layer. We convolved it so to get a convolutional layer. Then we pooled each feature map to get a pooling layer. Okay, so we'll get multiple maps. So that gives us the pooling layer, and then we flatten it. Okay, so until now we have three steps that are done. Now comes the ANN, which is a fully connected layer. Or so from ANN, if you all remember, when we built our architecture, we used the dense layers. Okay, so in the code lines, if you all remember, so in the layers module, we went and we used the dense layer. So a dense layer is a fully connected layer. So what is a fully connected layer? See, this is our input layer. This is our hidden layer. Okay, this is our input layer. So the each neuron, right, in the hidden layer, each neuron will be connected to each of the input neuron. So this one will be connected to this one will be connected to this one will be connected to this. Similarly for this one, okay. So it will be connected to each of these input neurons for this one and this one, okay. So this particular, section is called a fully connected layer because each hidden neuron is connected to every other input neuron. All right, simple, right? So okay, so that was about fully connected layers. Okay, fully connection is basically like saying that even the next layer, okay, this is the output layer, will be connected to each of the neurons in the previous layer. Okay, so that was about fully connected layer. Now, uh, oh, yeah, okay. So this was okay. So previously we had a flattened layer, which I told will be passing to our ANN. So this is our ANN. So if I remember, input layer. Okay, this is the hidden layer. Here we have two layers within the hidden layer, and we have the output layer. So what we do is we pass the flattened 1D array, okay, as the input to this ANN architecture. Now it will basically analyze, okay, analyze in a sense, it will try understanding the data. Okay, now say suppose we passed the data, and for this particular pass, this node had a so you know a particular neuron has activation function which gives us an output, right? So say suppose in this case the activation function, okay, once you applied it, gave us an output of 0.9. Okay, this one gave us a 1, this one gave 0.2, 0.1, 0.2, 1, 0.1, 0.1. Now maximum values are highlighted. For example, 0.9, 1, and 1. Okay. Now this is during the training. Okay. So we pass the input set of the training data, and the model already has what the actual output should be. So it should be a dog. So what it does, it notices. So it sees, okay, since the output is a dog, okay, since this neuron is activated, what neurons in the previous layer are activated for this neuron. So it will look, okay, so this one has a higher value. That means this is activated. So this, and this. So it remembers, okay, this three are activated when it is a dog. So it will store. So similarly for cat as well, okay, if you go here. So say suppose there's a training in the data set, we have input for a cat, okay, and it activates this neuron, one, two, three. So this cat new. So what this new model will remember is for this outputs, it basically triggers a cat. Okay, it basically implies that it's a cat. So as the training goes on, it learns. Okay, it learns what neurons are being activated for what particular output. Output in a sense, what like for what uh, neurons activated, what should be the next neuron that's activated. So say suppose this neuron and this neuron and this neuron activated. So maybe the model learned, okay, when this three are activated, that means this one is going to have a higher value and this one is going to have like a, say a mid value, say a 0.6, 0.5. Okay. So that's how the model will learn over time. So as we give it the input data, so if you see this is the image of a dog, we convolute it, we basically pooled it. Then again, if we wanted, we could convolute again, we could pool it again. Then we flattened it, okay, and then we passed it as the input layer, okay, to the ANN or to the fully connected, or you call it a fully connected layer for this particular for a single layer. Okay, this entire thing is full connection because all of them are connected to each neuron of the previous layer. Okay, so what it is passed the 1D array, it processed, it learned. Okay, then this is okay, just ignore this. It learned the data and then a model was ready. Okay, it was ready to be used. So this is just a summary. Okay, you all can go through this. Let's take a 5 minute break. After this, I think it's about softmax function and cross hydro. What I'll do, right? I'll do this at the end. Okay, I'll do this at the end. After this, we'll jump into the code. All right, because this is like additional. Okay, this is in depth for the cost function. So we'll take a 5 minute break. By 11:30, we'll start. All right. Hello. When did I get disconnected? Hello, hello. Where did I can't hear? Okay, now tell now. When did I end up getting disconnected? How long has it been? Oh, uh, what was the last part that I explained? You all remember? Oh, that's way back. Okay, okay. What we'll do, right? We'll take a 5 minute break because I talked for quite some long. I need a break. By 11:30, we'll start again. I'll explain again. I actually finished explaining the entire architecture, and I was supposed to be doing the code, starting with the code at 11:30. Anyways, 11:30. I'll what was I think so. Did I finish explaining pooling? Oh, so that means the entire thing is remain. Okay. Anyways, the thing is, my mobile gets heated up quite quick. Okay, and it switches off the hotspot. So because of that, it keeps getting disconnected. Yeah, I realize that. Next time, just give a call, alright? To the because I can't see the messages while I'm present. Oh, people left. They're gonna join back because I don't think I'll be able to complete. The thing is, it will keep getting disconnected and clean. I missed what you just said. So I was saying it will end up getting disconnected every now and so the pooling layer is not done, right? Can you all hear me? No. All right. You can hear me, right? Am I audible?
Yeah.
All right. So what I'll do is I'll present the. So the drawing part was done, or did I get disconnected in between while I was doing the illustrations?
If I remember correctly, it was feature detectors that Matrix was, which was the last thing, and just before the uh, leopard and cheetah pictures.
Oh, let me see whether I reached over here and that leopard cheetah is yeah, over here. Okay. This part was done. Relu.
Yeah.
Okay. Okay. So okay, I'll draw that again.
Maybe if you could just give a small recap of the ReLU part, like
Okay. So ReLU is like basically to remove any leniency. So if you see here in this particular image, okay, see this is an image of a building. It's a grayscaled image. Basically, colors that are in the range of white and black and in between grays. Okay. Now, if you focus on this particular edge over here, it will see a linear pattern. So it goes from white to black. Okay. Now you see here, white are positive numbers, black are negative numbers. Okay. So when what see over here, it's like a linear pattern. Okay. So if you see white is positive, black is negative. So it goes from positive to negative. So if the model learns this pattern, what it will every other space, like if we consider here, okay, it will try finding that particular pattern. Say suppose the model learned on this pattern, okay, because see in this entire image, this is not the only place where it's linear. It's linear over here, it's linear over here, it's linear over here, over here. So it's linear even if you see over here. So if the model tends to learn, okay, tends to get trained on this particular data, then say suppose you give it an image, right, as that has an input, okay, of this section. If you all can see where what I'm highlighting, okay. So say suppose it gives we give it an input as this particular section. Then over here also it will try to find this linear pattern. And if it doesn't, it will either like if it doesn't, then it will end up giving wrong results, or it might end up like if it learns on this, it will end up being too much fitted towards the training data. Okay. So, like it will try to find or classify the data that match to the training data. It won't be able to learn some or predict something that isn't present in the training data set. Okay, it will only be limited to like training data. So we call this particular case as overfitting, where the model is like highly attached to the training data. Okay. So, in order to break this leniency, or in order to prevent the model from learning this particular pattern or trend, we apply rectified linear unit. So, what does the rectified linear unit does is it basically removes the leniency. So, if you see in the previous this image, we had black over here. In this case, there is no black. Okay, all are either white or shades of gray that are more closer to white. So what we did was we applied rectified linear unit. So this is this particular graph, okay, the red one. So this is the graph of the rectified linear unit. Visible, right? Okay. So here what happens is
yeah.
all the values before zero. This is zero. This particular here, if you see it's zero on the x-axis. So for all the values, okay, of x that are less than zero, that are negative, in other words, have a y value that is zero. Okay, so it's like basically nullified. So we don't have any black values or negative values. Whereas in case of the positive values, the values greater than zero, it has a corresponding y value. Okay, so in that way, we have eliminated the leniency pattern or the black, and we only have whites and grays. Okay, so in this way, the linear pattern formation is basically avoided in the image or when the model goes to learn the data. So next time when an input is given, the model will be able to basically predict, you know, what kind of. Did I get disconnected? Because on my mobile it's showing that I left. Yeah, I'm getting disconnected again. I really don't know what to do because the Wi-Fi isn't there.
Basically, like the part where it's expecting the black values after the white, like negative after the positive.
So
That is
all
the
the
linear part. So
yeah negative values are basically eliminated while keeping in the positive values. Now yeah yeah.
so after that,
So once that is done, so that was like the sorry, I didn't.
Yeah, I mean, so like, what would be going on after that? Like after now?
Okay, so once that is
Okay,
done,
so
we
once
move towards cooling. Okay, I'm very-
okay, I'm very good.
Tell me one
Acha,
thing.
okay.
Tell me one thing.
Uh,
Uh,
what should I record the entire session? Because I don't think there's any point of like being disconnected again and again. Because you all won't understand. Yeah, the flow keeps breaking. So should I record? Because see, it's almost. I think it's 1 hour past, and we are still on the first layer. So should I record and upload? Because already there's a lot that I'm like a lot of content that I'm recording, but there isn't Wi-Fi, so I can't upload because it takes a lot of data. Mobile data gets consumed. I'm on both the mics were
both
off
the
and I'm
mics were off and I'm talking.
wait, just give me a
Wait, just give me.
okay. So what I was saying is, should I record and upload it on YouTube? Because I don't think y'all are understanding. Because the thing is, the flow is breaking again and again. Already there's a lot of content that I have to post, but again, Wi-Fi isn't there.
Yeah, cool.
Okay. Because it's almost an hour, and we are still on the second layer. Sorry for the inconvenience, though. Can't help it. The Wi-Fi isn't there, so everything gets messed up. So what I'll do is I'll
Nah, nah,
record it.
chill.
Yeah, I'll record tomorrow morning. No, I'll try to upload the video. Okay, whenever I'll get time, go through it. Is it possible? Okay, when are third year? When are you all free? For offline? Because online till the Wi-Fi gets fixed, I don't think it's possible. Third years are there, right? When are you all free? Hello, audible?
Yeah.
Tomorrow after 5. Okay, works for me. Okay, 5 to 6. Okay, where do you want to have the lecture? Because I don't know about any. I don't think the classes will be open after 5. The main gate of the building. For first years, also first years when I got free.
Again, I'll say evenings. I mean, tomorrow I would be free, but I
If
can't
it's
say
open,
like specifically what.
I just wanted to take the course to finish up with the course. If the classes are open, then we can have it in the classroom section. But is it possible for everyone to stay after 5? For those who are in hostel, I think it will be possible. But for those who aren't, I'll put a poll on the group. Okay. What I'll do, I'll record the session. I'll upload it. Okay, the session is actually recorded. Okay. So the thing is, I have recorded the session. I'll upload it. As and when it gets uploaded, you can go through it. Okay. After that, the codes are already there. I'll upload the data set as well. Uh, yeah, and then tomorrow after 5, okay, if people are willing to stay or whoever are like those who are there, I'll take a session for you all offline. Then we'll just run the codes and get things done. So by tomorrow, I'll try to finish. So for the offline, what I'll do, right? I'll do our ANN, whatever in terms of accuracy. I'll do the CNN, okay, and after that, I'll do that particular problem statement that I give. All right. So we'll do that. Yeah, cool. That's all. Okay, you all can leave now. I'll record the other part and I'll post it. The code part. Chalo,
Cool.
chalo, bye.
Yeah.
Good night.